homochirality by crystallization of an RNA precursor on a magnetic surface. And Furkan's bio, here we have right here. So Furkan received his BSc in physics in 2018 from Bilkent University in Ankara, Turkey. He then started his PhD in physics at Harvard University, where he focused on constructing an erbium quantum gas microscope in the group of Marcus Greiner. In 2021, Furkan shifted his research interest to the origins of life and joined the group of Dimitar Saslov at Harvard University. Since 2021, he has been primarily investigating the origins of biomolecular homochirality. All right, and with that, I'll stop sharing.
All right, thank you for the introduction. So let me share and make sure everything is good. Settings, it should be good now. Ish?
Yeah, looks good.
Perfect. All right. Thank you for having me here. And as Albert kindly introduced me, I will talk about the homochirality problem. So the premise is I will try to satisfy the molecular biologist's dream and everyone's dream who is working on the origins of life, which is to have a pool of enantiomer beta right-handed ribonucleosides. And by the end of my talk, I'll try to convince you that magnetic mineral surfaces can partially fulfill this dream. I'll start with the introduction of the problem and the mechanism we approach this problem with, and then the two experimental results, and then a theory perspective paper on the propagation of homochirality. So I'm sure the expert audience here is aware of what homochirality is, but briefly, in biology, left-handed amino acids and right-handed sugars and nucleic acids are ubiquitously used. And although there are two possible combinations of these biomolecules, life is extremely picky when it comes to chirality, and it selectively uses these molecules. And this behavior is omnipresent in all living systems. And this is what we call the biological homochirality. And the mystery is we don't know what triggered this symmetry breaking and what made life choose left-handed amino acids and right-handed sugars and nucleic acids. And this is really a big problem in the origins of life research. And this is the problem I address with my research. So it's kind of customary to break the problem into two parts after Frank's seminal paper. The first part of the problem is a symmetry breaking agent that couples to chirality and introduces a small bias that kind of nudges a racemic mixture, an equal mixture of left-handed and right-handed molecule to one direction. And then it induces a small chiral excess. And then the second part of it is that this excess gets amplified to reach homochirality at this compound. And we can kind of add a third part to it, which is that, after you establish homochirality at a compound, the established homochirality should be spread to the other parts of the network, because it's important to make one molecule homochiral, but it has to be that the whole network is homochiral. And of course, there has been a lot of, work on this problem before, and I will mention three important approaches. And the first one is kind of applying the idea that was, found by the SOI reaction to the prebiotic, molecules. So kind of finding an autocatalytic network that is asymmetric. And people have been working on this with this approach. And then the second part is people tried to use circularly polarized light as a way of breaking the symmetry. And circularly polarized light is available in space, and this has been measured. And this approach can explain the bias of, the chiral bias that is found in meteorites. And then the third one is the Wiedemann ripening, which requires solution phase racemization. And as far as I'm aware of, in the prebiotic chemistry, it's hard to find such a constraint. So now I'll come to our approach, and I kind of want to give you a premise that, by the end of my talk, I'll explain I will have explained a symmetry breaking mechanism and a simultaneous amplification to reach homochirality at a compound. And then I'll introduce a mechanism such that the attained homochirality at this compound can be propagated to achieve a systems level homochirality. So without further ado, I'll talk about the chiral-induced spin selectivity effect. And this is the effect by which we break the chiral symmetry. And chiral-induced spin selectivity effect has actually been discovered recently, roughly 10 years ago. And this seminal experiment kind of shed light on the spin chirality interactions. And I'll explain what this experiment is about. So in the original chiral-induced spin selectivity experiments, what people did is they put a monolayer of double-strand DNA molecules on a gold surface. And gold is not ferromagnetic, so it doesn't have a bias in its spin alignment. And they ejected light from this gold surface by applying light. And due to photoelectric effect, electrons are ejected from the surface, but their spin had no alignment after they got ejected from the surface. However, after they go through the monolayer, the chiral monolayer, the bias in the spin alignment of the electrons were along one direction with a very strong polarization, up to like 80%. So essentially, the chiral molecules acted like a filter for the spin of the electrons and only allowed for the transmission of one spin state, but not the other. And then when they changed the chirality of this monolayer from right-handed DNA to left-handed oligopeptides, they observed the opposite spin polarization. And they kind of established with these experiments that chiral molecules strongly interact with the electron spin. And this is the takeaway message of the chiral-induced spin selectivity effect. And I'll try to kind of delve a little bit more on that without going too much into the theoretical aspects of the cis effect, chiral-induced spin selectivity effect, because it's beyond the scope of this talk. But the important thing to realize is the cis effect establishes that electron transport, electron transport through a chiral molecule is spin selective. So essentially, if you transport charge inside the chiral potential of a chiral molecule, the charge polarization gets accompanied by a spin polarization because of this effect. So a left-handed molecule will have opposite spin states on its two charge poles, and the other handedness, the right-handed molecule, let's say, will have the flipped one. So essentially, because of the cis effect, the charge polarization inside a chiral molecule gets accompanied by a spin polarization. Okay, so how can we make use of this, right? So in the original cis experiments, people use chiral molecules to filter spin, and that's what they established. But what we kind of want to do is, utilize the cis effect in the reverse direction. We don't want to select spin based on using the chirality, but we kind of want to bias chirality using the bias in electron spin. So kind of using the cis effect in the opposite direction. And now I will explain how magnetic surfaces with a net spin alignment can function as chiral agents. Okay, so imagine a surface with a net spin alignment as shown here, and imagine a racemic solution of a chiral molecule, right? Equal amounts of left and right-handed molecules. So then, as these molecules kind of approach the surface because of the van der Waals forces, the dispersive forces, the molecules gets polarized, charge polarized. And this is an induced charge polarization. And it's a transient one, right, near the surface. And the molecules will approach the surface from a kind of a moiety that has the affinity to the surface. So it will be identical for the left and right-handed molecule. And the charge polarization, therefore, will be at the same pole for left-handed and right-handed molecules. And what does charge polarization mean? Charge polarization means that you redistribute the electron density inside a chiral potential, right? You move charge from one end of the molecule to the other, which means that you move charge inside a chiral potential. And that's where the cis effect, plays its role. And as you move charge inside the chiral potential, you also filter out electrons based on their spin state. So for, let's say, left-handed molecule, the up spin state will be predominant in this end, and the down spin will be on the other. And for the right-handed one, it will be the opposite. Okay, so that's how they differ. And now the effect of magnetic surface will, do its job, and the surface spins will start to couple with the molecular spins. And you see already that one enantiomer couples with the surface like it's a singlet state. It's an up-down coupling, and it's a energetically preferable coupling. And for the other one, it will be the triplet-like coupling, up-up coupling with the surface, and that is an energetically kind of penalized coupling. So essentially, the magnetic surface kind of pulls one enantiomer and increases its local concentration on the surface and pushes the other one, thus breaking the chiral symmetry at the surface. So that's how magnetic surfaces function as chiral agents, because of the spin exchange interaction with the charge polarized chiral molecules. All right, is this enough? Because this is a short range interaction. This is a spin exchange interaction, and it requires the electron densities to overlap. So it's really short range. We have to be able to propagate the kind of attained bias, which is at the surface, to kind of into the bulk of the solution, right? So what is the way? The way that we came up with is using the conglomerate crystallization. So there are two types of crystals, chiral crystals. The more common version is the one on the left. It's called racemate. A unit kind of includes right-handed and left-handed enantiomers in equal amounts. And the less common one, roughly the 10% of all chiral crystals, are conglomerates. And they crystallize, as you see, in units where each unit is homochiral. So essentially, for conglomerates, if you kind of have a seed of one enantiomer, as the seed grows, it doesn't racemize. It kind of grows homochirally. So essentially, if you seed the crystallization using the spin exchange interaction coming from the magnetic surface at the surface, this attained kind of excess bias can be propagated by the conglomerate crystallization. So the conglomerate crystallization kind of allows for propagating the surface level enrichment to, beyond the surface. Okay, so how can we combine these both and kind of put these in a periodic context, right? We have to find a molecule that crystallizes as a conglomerate, and we have to crystallize this molecule on a surface. And moreover, this compound has to have some importance and relevance to periodic chemistry. So the compound we use is the one shown here in the box. It's called riboaminoxazoline, RAO. And RAO is a precursor to pyrimidine nucleotides, and it can be synthesized under prebiotic conditions from simpler sugars like glycolaldehyde and glyceraldehyde and 2AO, 2-aminoxazole. And it's a very stable molecule. It doesn't isomerize like sugars. It doesn't racemize. It's very UV stable, and it's a direct precursor to nucleotides. What does that mean? The attained chirality at RAO directly determines the chirality of pyrimidine nucleotides. So essentially, if we lock the chirality at RAO, we directly establish the chirality at nucleotides. So that's the compound we work with, and we started from its racemic solution, and we seeded its crystallization on a magnetite surface. Magnetite is an iron oxide, and it's the most magnetic and most commonly found magnetic mineral on Earth. And we essentially, the simple experiment illustrates how we did the experiments. We have a magnetic surface, and it's magnetized by a magnet, external magnet. And we put the racemic solution of RAO on top of this magnetite surface. And we obtain crystals of RAO on the surface, and we analyze their chiralities. So because the synthesis of RAO is also producing other steric forms of RAO, we first crystallized RAO and then recrystallized it, and we obtained the crystals of pure RAO, as you see on the right. And when we did this on a magnetic surface, we obtained very high enantioselectivity. The image on the left shows crystals of RAO that are nearly enantiopure on a magnetized magnetic surface, magnetite surface. The black background is magnetite. And on the right, you see the circular dichroism spectra of the crystals collected from the surface. So what does this spectra mean? The spectra is essentially showing the difference between the absorption of right-handed and left-handed circularly polarized light, and the presence of a signal indicates the presence of enantiomeric excess. So the blue curve is obtained when the surface is one spin state, and it shows the spectra for left-handed RAO, and the red spectra is flipped, and it corresponds to right-handed RAO, and it corresponds to the case where we done the experiment on a upspin surface. And of course, when you take the when you keep the magnetic field, but when you use a non-magnetic surface like silicon, the effect shouldn't be present because this is a spin-spin effect. It is not a magnetic field effect. And this control experiments and the absence of signal kind of proves this, right? It's important to mention again that we do not get the effect from just the presence of magnetic fields. Magnetic fields cannot introduce a chiral bias. They don't have a chiral property, so to say. But the spin effect, the spin-spin interaction that I explained before, can do it. So then we investigated, what is the lowest limit above which with a subsequent crystallization step we can reach homochirality, and we found that if you crystallize a solution with around 25% EE enantiomeric excess in the beginning, with a subsequent crystallization, you can reach homochirality. And you crystallize D on the upspin surface again, and then you can nearly get homochirality. And that's why we say homochirality in two crystallizations. So then, being aware of the fact that in a natural setting, we do not get a surface with nearly uniform like magnetization, we kind of try to investigate if the opposite effect would also work or not. Meaning, if we start with a sediment with a natural magnetization with a small bias, and if we grow homochiral crystals on it, the presence of chiral crystals, would the presence of chiral crystals on the surface flip the magnetization of the surface? So kind of, so as magnetic surface is choosing chiral molecules, can chiral molecules magnetize the surface as well? So we kind of investigated the chirality-induced magnetization of magnetic surfaces by chiral molecules. And this is very similar, in fact, identical physics-wise to the previous effect I have introduced. Just imagine a molecule. Now it's not a racemic case, but the surface is, so to speak, racemic. It doesn't have a net spin alignment. And when we crystallize a homochiral molecule on it, as the molecule approaches, it will have a net spin alignment on its end that it approaches the surface. And because the molecule kind of wants to have a singlet-like alignment, it flips the spins on the surface, thereby magnetizing the surface. So essentially, chiral molecules too can magnetize magnetic surfaces. And we have done multiple measurements to probe this effect, but because of the time constraints, I'm only going to show one. And this is a magnetooptical Kerr effect microscope measurement. And essentially, in this measurement, you reflect off a polarized light off of a surface. And by measuring how much the polarization rotates from because of the reflection of the surface, you kind of get an understanding of the surface magnetization. And this is imaging with polarized light, and the image contrast indicates a magnetization difference. So when you see shades on the images, that indicates magnetization difference. And in the experiment, we use a surface with no bias, and we kind of crystallize right-handed, in this case, REO molecules on the surface like a line, and we kind of observed how the surface behaves under magnetic field. And when we applied magnetic field in a region where there are the crystals, as you see in this white box, we observe different behavior than in the regions that are free. So that's interesting. So let's look into this a little bit more here. So we kind of took like a hysteresis measurements. Maybe people are familiar with these measurements from squid measurements. And this is essentially, measuring the magnetization properties of the surface. So in the central line, you see the regions that are affected by the chiral crystals because they're under it. And the other regions are kind of the free ones. So we kind of start reading this measurement from the left. On the left, we apply like a strong negative magnetic field, and we kind of magnetize all the domains. So red and blue curves that correspond to these two regions have the same, net normalized magnetization. And then as we increase or, flip the field in the opposite direction, at one point, we kind of increase the field until here, let's say 1.5 millitesla. And at this point, about this field, the free domains kind of give up and then flip their magnetization to plus. However, the domains underneath the chiral crystals are kind of protected by the added effective magnetic field provided by the crystals, so they kind of are more sturdy. The domains under the chiral crystals kind of persist more because of the added effect from the chiral molecules. And then, of course, if you increase the field beyond the point, they also give up and all of them gets magnetized in the same direction. And then you can kind of do the same thing in the opposite direction and start from this place and then go here. The free domains give up and then change their magnetization and the other ones do not. So essentially, the presence of chiral crystals kind of latches the domains underneath them and increases the magnetic coercivity of the surface. And because of the finite size of the magnetic domains, as you see, the regions that are not even covered by chiral crystals are also magnetized by the chiral crystals. So the effect is kind of like an avalanche, right? You put the chiral molecules and they magnetize the domains underneath them, and then the effect kind of spreads around as long as because of the finite size of the domains. And also they increase the magnetic coercivity of the surface by at least an order of magnitude more than the Earth's field, and kind of making the surface more magnetically strong. And this also ensures that the same chiral bias coming from the magnetic surface will be present in the environment in a persistent manner. And thereby, by showing this, we kind of show all two kind of open ends, the enantioselective crystallization part and chirally selective magnetization part. And when you kind of combine them in a feedback loop, you can kind of envision a self-reinforcing feedback that magnetizes the surface and creates a purer and purer spin polarized surface, and also induces, more and more pure enantio-enriched chiral molecules. So essentially, this shows the feedback between chiral molecules and magnetic surfaces in kind of on early Earth conditions. And although we do not point out a very refined geochemical scenario, we envision this being on like a shallow lake that is covered by magnetite deposits, like the one that was discovered in Gale Crater. And we envision a stream of racemic, RAO that is flowing slowly on this magnetic surface. And as it flows, the magnetic effect, the magnetization effect we established kind of can filter out the right, enantiomers because of the interaction, and you can kind of separate the right enantiomer on this zone. So I would like to highlight, and before I move forward to my last part, I would like to emphasize that the mechanism we studied is the highline, and the specific application of it on RAO is debatable, depending on what you want to do. And its application on an RNA precursor is just one application, and I can see way more uses of this asymmetric phenomenon. And now we are working on actually to show that a similar effect can be observed with other conglomerate forming molecules such as peptides. So my last part of my talk will be about a theoretical paper we just published, and it's called The Central Dogma for the Origin of Homochirality. How many minutes I have? Oh, okay. Few more minutes. Cool. Okay.
Yeah, you got
So
like 5 minutes.
5 minutes? Perfect. Good. So, okay, it's called Central Dogma for the Origin of Homochirality. And as you can imagine, it's inspired by Francis Crick's Central Dogma. So in this paper, we attempt to simplify a complex problem as inspired by Francis Crick's approach on the transfer of sequential information in biology, right? In his case, he investigates how the sequential information in DNA goes to RNA and then the proteins, but not backwards. So there is a unidirectional flow of information in biology. And we looked at how chiral information might have propagated in a prebiotic network as inspired by his coarse-grained, low-resolution look at a complex system. So this paper is not about the origin of homochirality, but about the propagation of homochirality and its direction. So now, as I will explain in a few minutes, the kind of direction that we propose starts from RNA. The chiral information kind of starts in nucleic acids, goes to peptides, and then to metabolites. So there are 3 molecular classes that we investigated, and we looked at what molecular class could be the ideal one to establish chirality at, such that the established chirality can be efficiently propagated to other molecular classes. Okay, so let's look into metabolites first. Okay, so here you see the Krebs cycle, and the colorful discs show chiral molecules, and the others show achiral ones. And as you can see, even though you can establish homochirality in the citric acid cycle by, let's say, from tartrate, which crystallizes as a conglomerate, and from its reduction to malate, you can make malate homochiral. But what happens next is malate either oxidizes to oxaloacetate or dehydrates to fumarate, and isocitrate also goes to achiral molecules. So in the absence of homochiral enzymes, Krebs cycle is kind of like a chirality grinder. You cannot propagate chirality because of the presence of achiral branching points at which you lose the chirality, even though you can establish it. So it doesn't seem to be effective to propagate homochirality within or from metabolites to other molecular classes. Okay, so it seems like metabolites is not the good place to establish chirality yet, in the absence of homochiral enzymes, which is the case for the prebiotic earth. What about amino acids? Well, there are 19 chiral amino acids, so there are plenty of them, and they have idiosyncratic chemistries. Their chemistries are not the same. And it's a tedious task, although it's possible, I don't rule that out, to make all amino acids individually homochiral in a common direction, meaning all of them to L, to left-handed. And there are some amino acids that I show here that crystallize as a conglomerate, and our mechanism can be applied to them. But first of all, it's not guaranteed that they will be in a common direction because they're different molecules. They will approach the surface from different ends, and we have to try it out. And second, what about the others? So it seems that it's a little bit of a tedious task. And if there's a more elegant way, that's better. And there seems to be an elegant way. So now check out this recent results by Longfei Wu from John Sutherland's group. And in this experiment, what they show is from a racemic pool of amino acids, if you make peptides using homochiral tRNA analogs, you can make peptides highly enantiomer enriched in the opposite direction of RNA, which means that L amino acids can be selectively attached to tRNA analogs composed of D-ribonucleotides with up to like 10-fold stereoselectivity. So essentially, you can transfer chirality from homochiral RNA to peptides, although amino acids are still racemic. Okay, and it is the right kind of the right stir selectivity. So D makes L and L makes D. And more recent results from Shostak group actually indicates, which are going to be published, that this phenomenon is actually very general, and it can be applied to more amino acids than Sutherland's group showed in this particular paper. Okay, so let's keep this link in mind and put it here. So D-tRNA can make L peptides. Well, L peptides can make L enzymes, and with an enzyme catalyzed metabolism, you can make homochiral metabolites. Okay, so then tRNA is composed of D-tRNA is composed of D ribonucleotides, and if you can find a common ribonucleotide precursor from which you can propagate chirality, then the entire problem of origins of homochirality can be reduced to making one compound homochiral, from which then the chiral information can be efficiently propagated. And this molecule, as we show, can be RAO. So essentially, you make one molecule homochiral and then propagate it to the entire network with this in our proposal. And interestingly enough, the direction of chiral information flow here resembles the flow of sequential information. It still flows from nucleic acids to peptides, basically. And so it kind of is, as established by central dogma, it seems like that it's the genetic code is the right place to establish chirality. So I'll summarize now our results. In my first paper, we provided like a perspective of how asymmetric processes can take place on early Earth due to this effect. And in the experimental results, we have established this phenomenon in a series of 3 papers. And now what I'm working on is showing that this can be done with real natural magnetic minerals that we synthesize either in the lab or we collect from the nature. And this will be the next. And with this, I would like to end my talk and thank my advisor, Dimitar Sasalov, who is holding a natural magnetite rock from Tumbiana Formation in Australia. And I guess Dimitar is here today. And also I would like to thank my collaborators, the groups of John Sutherland, Ron Nauman, and Josip Altiel. And I would like to answer your questions.
All right. Thank you very much, Furkan, for that amazing talk. I'm sure there's tons of questions, but as always, ask you, members of the audience, to write them down or make a mental note, and we will open up the questions at the end of the next talk.
Perfect.
All right, so thank you very much.
Good. Am I on time?
Close enough.
Good.
Okay, so now I will introduce the next speaker. So our next speaker for this session is Shotaro Tagawa. He's a PhD student at the Earth Life Science Institute at Tokyo Tech in Japan. And his talk is titled Prebiotic Organic Phosphorylation in Deep Sea Supercritical Carbon Dioxide Water Environment. So Shotaro Tagawa is a PhD student, like we said, at Tokyo Tech. He obtained his BS in Control Engineering from Kyushu Institute of Technology in 2018 and his master's in neuroscience from Osaka University in 2020. He joined LC as a PhD student in 2021 after leaving his job as a recruitment agent. He is tackling the role of liquid supercritical CO2 fluids in pools under the seafloor and the origin of life, and his current work is focusing on phosphorylation in sea hydrothermal systems. All right, so with that said, I will stop sharing my screen and Shotaro, take it away.
Thank you. Can you see the? Oh yes. Okay. Let's go. Hi everyone. I'm Shotaro Tagawa, a PhD student at LC in Tokyo Tech. Today I'll be talking about the prebiotic organic phosphorylation and deep sea supercritical CO2 and water two-phase environment. Where is the birthplace of life? So far, many researchers have tried to tackle to this mystery. a multitude of birthplaces have been proposed, including, of course, other locations outside of the places you see on screen. Regarding RNA and its precursor synthesis, such as nucleotide and nucleoside, I think a lot of research has been focused on terrestrial hot springs, like Darwin found. In particular, phosphorylation reaction leading to prebiotic nucleotide synthesis have been reported from conditions simulating wet-dry cycle near terrestrial hot springs interacting with the atmosphere. In many cases, the conditions involved urea and cyanogen as a catalyst or other reactants. The advantage of having an atmosphere is that water can evaporate from the aqueous phase, which results in the condensation of various organic molecules. To demonstrate this, here are some previous studies tackling nucleoside phosphorylation. The phosphorylation of nucleosides under potentially prebiotic conditions has been attempted using catalyst or reactants and then drying up for the condensation of the reaction solution. When using phosphate minerals, some solution or reagent is used to dissolve phosphate from the minerals. Thus, condensation and drying is very important for prebiotic chemical evolution. And now, what about in an ocean world? Deep sea environments are one of the plausible birthplaces of life. However, it's considered molecules will undergo hydrolysis due to the presence of abundant water. Essentially, water is wet. We need to escape from the water world. In the past 20 years, natural CO2 fluid have been discovered in deep sea hydrothermal fields, such as Okinawa Trough and Mariana Arc, right, showed by these bubbles and droplets. Modeling shows that subsurface pool of liquid and supercritical CO2 exists. CO2 has a critical point located under the mild temperature and pressure conditions around 31 degrees Celsius, 70.3 megapascal. Supercritical CO2 is known as a nonpolar hydrophobic solvent. In general, supercritical fluids have unique characteristics of liquid-like solubility and gas-like diffusivity and low viscosity. So far, supercritical CO2 is mainly used in the industry as a green solvent to dissolve various hydrophobic molecules like caffeine. This is an example of prebiotic chemical evolution under SCCO2 and water environment. Mayer's group proposed SCCO2 environment in deep strike slip fault zone in exposed plot continents. Vesicle formation process in this environment facilitates the condensation of amino acids for peptide synthesis. Hence, recently proposed liquid and supercritical CO2 hypothesis assumes that two-phase SCCO2 and water drives prebiotic chemical evolution near the deep sea hydrothermal system. The aqueous phase adjacent to the CO2 fluid is assumed to be highly acidic and thus dissolves various ions such as phosphate from apatite minerals. In such environment, phosphate will be accessible and further undergo dehydration and condensation to drive phosphorylation. We subsequently experimentally experimentally tested such possibility. We use nucleoside as a target for phosphorylation by using general analytical instruments such as synthesis via phosphorylation reaction in the HCl2 and water two-phase environment. Water is released from the water droplet, and the reaction solution is concentrated. We have developed a hydrothermal reactor system using an autoclave to achieve the phosphorylation reaction in HCl2 and water system. Nucleosides were mixed with a phosphate source and other chemical reagents, and the solution was added to the inner cylinder. The solution was then flash frozen using liquid nitrogen, and then liquid CO2 was injected on top. Finally, the reactor was heated by oil bath under different temperature, pressure, and duration as shown here. Samples were subjected to UPLC and LC-TOF-MS analysis. First, we performed nucleoside phosphorylation using origin nucleoside, sodium dihydrogen phosphate, and urea. The reaction condition were 70 degrees Celsius, 10 to 12 megapascal, and 24 hours. This condition is the base condition. And this is the result. Accordingly, we observed origin phosphorylation under the HCl2 environment only with urea greatly enhanced the reaction. Here, the chromatography and MS spectrum shows that several isomers of origin monophosphate were identified only in the presence of HCl2. For the negative control of HCl2, we checked the yield of UMP in the water-rich environment using gold tube. UMPs weren't identified in negative control. We further investigated origin phosphorylation using 50 milligram hydroxyapatite as the only source of phosphate. We observed similar yield UMP isomers compared to the experiment using sodium dihydrogen phosphate as a phosphate source, which suggests that phosphate is indeed released from apatite and further used for phosphorylation reaction. Phosphate assay shows that around 2 millimolar phosphate dissolved from 50 milligram hydroxyapatite. Around 10 megapascal more CO2 dissolves into water and thus lowering the pH to around 3. It has been predicted that the pH of an aqueous solution coexisting with CO2 fluid becomes highly acidic. At this acidic pH range, hydroxyapatite is known to dissolve in water. Most recently, we investigated the temperature dependence of nucleosides phosphorylation. Origin phosphorylation proceeded over 60 degrees Celsius in HCl2 condition. The yield of UMP can be higher with increasing temperature. High temperature are likely to cause UMPs to decompose, but we can't understand the result now. We are currently preparing experiment to collect data and collect data of thermodynamic parameters to make theoretical predictions. We have also performed a comparative time course experiment using 4 different nucleosides to understand the difference in their reactivity as well as the duration needed for the reaction to reach equilibrium. As a result, UMP has shown its maximum yield to reach 17% after 120 hours, followed by CMP and GMP in that order, whereas the yield of AMP was the lowest for nucleotides after 120 hours. The overall trend suggests that reaction rate differs among nucleosides, perhaps due to the difference in the pKa and or reactivity with urea, etc. And we conducted a time course experiment of origin phosphorylation from 1 to 240 hours. We don't have data between 120 and 240 hours, but the yield of UMP is expected to have almost reached equilibrium for after 120 hours. The synthesis of UMP was confirmed after 21 hours. Some research simulating wet dry cycle terrestrial hot springs showed that the yield of nucleotide were increased even after 120 hours because our reaction condition was sealed environment and additional reagent wasn't added during the reaction. Equilibrium may have been reached after 120 hours. Finally, I'll talk about urea fraction for this reaction. Previously, two different reaction mechanisms has been proposed. A model by Sutherland suggests that urea is directly reacting with phosphate to form reactive urea phosphate intermediate to be attacked from the nucleoside hydroxyl group to form nucleotide. Whereas Katsura and Inagaki proposed that urea first decompose into isocyanate and ammonia, in which isocyanate further react with phosphate to yield carbamoyl phosphate, which again reacts with the nucleoside to form nucleotide. We then tried to detect urea phosphate intermediate as well as carbamoyl phosphate using phosphorus NMR. However, we could not observe a signal indicating such compound. We then went back to the UPLC data and found a mysterious unknown peak that did not overlap with non-standard chemical compounds. Interestingly, LC-MS analysis revealed that this compound had the M/Z of 288.1, which is equivalent to the mass of carbamoyl nucleoside. The same results are confirmed by 4 different nucleosides. In addition, experiment used with carbon-13 urea has showed that this isocyanate was from urea. Therefore, we are now further investigating the possibility that this compound could be the key intermediate to be phosphorylated. In summary, we confirmed that two-phase HCCO2 and water condition can drive phosphorylation reaction both from sodium phosphate as well as hydroxyapatite as a phosphate source. Increasing of temperature can enhance nucleotide yields. Time period of the experiment has shown difference of reaction rate and final yields among 4 nucleosides. We lastly found that carbamoyl nucleoside intermediate is formed during the reaction process, which may lead to new reactions reactions model. Finally, I'm thinking the role of the CO2 and water two-phase environment in the origin of life. We confirmed that this environment can dissolve ions from mineral and concentrate the reaction solution. I think that this site may have served as a place where molecules involved in the synthesis of biomolecules were extracted from the various minerals and magmatic gases under the seafloor, and potentially where these molecules were concentrated. However, there are many unknowns, especially the element involved in the origin of life distributed in each phase, and the stability of organic and biomolecules in this environment. Therefore, we will address these topics in the future. I've talked about many things today, but the battle against water world is far from over. I hope to find a world where we can coexist by understanding water world. I would like to especially thank Associate Professor Fushima and following 3 students who mainly supported my research. Thank you for listening. Oh, sorry, it's very short.
Waterworld is one of my favorite movies. Okay. So now we'll open up the floor for questions, and the way we do that usually is you can either type your questions in the chat, or you know, if you would prefer to just on your mic and ask your question, that's also okay. But just raise your hand if you want to do that, and we'll open up the mic for you. So we have a question from Kevin Devine right off the bat. Go ahead, Kevin.
Anyway, thank you, Furkan and Shotaro for 2 fascinating talks. So I've got a question for both of you, starting with you, Furkan. I mean, if you think of amino acids and you think of and sugars, they're quite different molecules. You know, the amino acids, you've got a very large dipole moment. You've got 2 ionizable functional groups. Do you see this preferential crystallization? Is it more efficient with these sort of amino acids with higher dipole moments than it is with the sugars?
Interesting question. Thank you for this great question. So yes, it's about how efficiently you can polarize the charge, right? And actually, it seems like that it will be the case because people have measured spin polarization in molecules because of charge polarization, and they obtained much higher spin polarizations with oligopeptides than they did with, like, let's say, DNA. So I expect more efficient crystallization because of higher spin selectivity with peptides than sugars, let's say.
Right. Okay. And you know, the fascinating thing when you said that, you know, the basically dRNA, basically it crystallizes, it sort of like binds to L amino acids. Right. Is it the same the other way around? L RNA with L ribose, does it bind more efficiently to D amino acids? Is that
yes?
So is it the same efficiency as well? Is it?
Yes. Nearly the same efficiency. I mean, of course, within the experimental errors, but yeah.
I mean, that means now I would honestly think if given magnetite, hematite, how sort of like relatively cosmically abundant they are, we are going to see the life as we know it with L amino acids and D sugars, I would say. That means the problem is if in, say, Jezero crater or Gale crater, we find L amino acids in abundance, we cannot therefore say that they are biogenic in origin. I hate to say it, but that's what it seems to me.
Well, that would be lovely, yeah.
Okay.
Yes. Your intuitions are all, you know, great. And I agree with them. Yeah.
Indeed. Thank you. Fascinating talk. And
Thank you.
Shotaro, your water supercritical CO2, what was the pH of your aqueous solutions? Were you able to vary that at all? And if so, what effect did that have on the yields of your nucleotides?
During the reaction, the pH maybe around 3, and before the experiment, the solution the pH of solution is around 4.
So it's quite acidic. They're quite acidic then. Yeah. Right.
And maybe it's ambiguous, but after experiment, the pH become around 7. I think the urea decomposed to to ammonia.
Okay, right. Okay, it's interesting because then that will have an effect of whether you produce your carbonyl nucleosides. That will certainly affect the relative yields of those at different pHs. And it's not easy actually to go from the 5' carbonyl nucleoside to the nucleotide. That's not an easy thing to do actually. Under those conditions, I wouldn't have thought. So, but it's interesting that you've clearly got evidence that you've got that as a side product. That's interesting.
Yeah, thank you.
Okay. Thank you very much anyway, guys. Thank you. That was great.
Thanks.
All right, thank you. There are some questions in the chat. I have a question of my own just to start. So this one is for Furkan. I noticed you had other diastereomers of the amino oxazolines, and of course you get those by reacting with glyceraldehyde with 2-aminoxazole. I was wondering, do you see your mechanism as a way to achieve diastereoselectivity?
Okay,
especially
good.
with respect to that or like other sugars?
Okay, so good. Yes and no. Okay, so in our case, the stereoselectivity is kind of trivial because the other steric forms are much more soluble, so they don't crystallize in the same time frame as RAO does. So it is not about the magnetic surface; it's just pure dissolubility difference. Okay. So in our case, it's like that, but the spin exchange interaction should also affect those things in a different way as well. But we have not tested that because in our case, it was not necessary.
Okay. Yeah, I can definitely see the broader application of your work though. It's really fascinating.
Yeah. Thank you.
So I'll go ahead and read a question from the chat. This is from Kelly. And if you like, you can read along too, I guess. So this is a question for both presenters. Are you familiar with biofilms, benthic mats, and or microbial processes that use urea, nitrogen, phosphorus, and other nutrients as energy source? Could the crystallization be similar to conditioning surfaces for biofilms, mats to form, and have different surfaces been tested to see what happens?
I guess the first one was more for Shotaro. Shotaro? Do you want to answer that first?
Okay. Sorry, I don't know about biofilm. Sorry, I don't know. Sorry, I don't have idea.
So yeah, in the second case, well, I can say that I don't think it's similar because here the main thing is just a spin exchange interaction with the magnetic surface and the chiral molecules. Although I'm not exactly familiar with the benthic mats or biofilms, but I can answer the second part of your question better. Yes, we tested the mechanism with different surfaces, but more synthetic ones before we switched to magnetite, which was actually kind of a technical challenge to switch to magnetite, but it was easier to work with like nickel or iron or cobalt surfaces, and the mechanism works same way, like as long as the other surface doesn't react with your chemicals. If it just comes down to magnetism, it works the same way, but you can come up with a surface that is magnetic, but it may react with your reagent, then it won't work, of course. And I can definitely send you papers on that.
All right, fantastic. So next we have another question for Furkan. Is crystallization instant? Does the time to crystallize have any significant impact on chirality?
Right. Yes, good insight. And the answer is yes, the time has significant impact on the selectivity because this is a kinetic effect. This is not a thermodynamic effect, right? If there was an absolute energy difference between D and L enantiomers, then the problem would be much easier. So kinetic effect means that one enantiomer crystallizes faster than the other one, right? So there is a peak time. Well, there's a time at which the EE, the enantiomeric excess, is largest. And if you wait ad infinitum, then you would get zero. Because if you wait everything to crystallize, well, if you start with a racemic solution, you will get racemic crystals, right? So yes, there's a time.
All right. And the next question is for Shotaro. Can we use supercritical CO2 / water for better growth of rhizobacteria, which promote plant growth?
Sorry, where is the question?
Oh, it's in, if you open up the chat, you can,
Yes,
it's the third question down.
From Kerry, no.
Oh, wait, sorry, this is a direct message to me, sorry. I can paste it to everybody.
So sorry, I couldn't catch what the
Yeah,
image.
one second. Okay, now I think you can see it's the latest question.
Okay, can we use CO2? What is CO2 water for better growth of bacteria which promote plants growth? Plants growth. I think it's difficult because because pressure is high and pH become very high acidic. So I don't know this bacteria can live in the environment. So yes, I think so.
Right, yeah. Interesting question. Another question for you, Shotaro. Actual deep sea vents would also be under pressure. How do you simulate the similar amount of pressure in lab? Are you doing lab simulation at atmospheric pressure?
Doing pressure. Sorry. Maybe this one. No. Yes. I maybe one. In general, about over the depth of 1,000 meter is 10 megapascal, and but yes, but yes, it's general information, but I don't know how to check the pressure, and I in my lab we don't doing lab simulation at atmosphere pressure, and I simulate. Is it answering your question? Yeah.
Well, I guess your experiments are already under pressure in the hydrothermal reactor, right?
Yes, yes. I check the pressure using analog pressure meter.
Yeah. They're already under similar pressure, I think. Yeah. We have a hand raised, and so Wataru, please go ahead and turn on your mic.
Oh yeah, can you hear me? Thank you
Yeah.
for us talking for those peoples. I'm very interested in the talks. But I have the first of all, I'd like to reply for about the questions. Can we use the supercritical sheets water, the formulas? I think, in my opinion, the supercritical sheets using is the maybe difficult because it lowers the flux of elements that makes up the carbonates, for example, calcium and magnesium. So, but if those effects are right, it might work. But I don't know if rhizobacteria can live in the high temperature pressure conditions where supercritical sheets can exist in the first place. So, and I have a short question to the Shotaro on the. In your figures, I'm curious as to why the lava is larger at 72 and 120 hours, but smaller at 240 hours. What does this mean if it is converging to some steady state? The transition to the steady state, can you explain why the error becomes larger in the middle phases?
Sorry, Takagi-san, is this my question? and so,
I'm wondering the Rava, can you show the slide again? Oh, okay. I sent to you
sorry.
From the chat. Okay.
Thank you.
I send now.
I'm curious. Thank you. I'm curious as to why the error is large. Large about us. What does this mean? I think if it is covering to some steady state, can you explain why the error becomes large in the? I think there are two reasons, and one is the changing range, changing area to how to say it's sigmoid curve and sigmoid curve and upping the area is around 72 hours, 2 hours, and other reason is my experiment equipment. This system is how to say it's a static. There's some little vibration of increasing temperature. So I think it's give the result some effect. it's my answer.
So the temperature is not completely homogeneous at all times. I think is that way.
Very yeah, waving.
Wavy temperature.
Yes, but so now I use mount heater to control the temperature with PID control. It's very smoothly changing the
Okay.
temperature.
Yeah. Gotcha. Let's see. I have another question for Furkan. I was just wondering, in a realistic prebiotic setting, you might have lots of salt in your slowly evaporating
Right.
pond, and would salt kind of prevent some of these molecules from sticking to the surface?
Yeah, that's interesting, right? I mean, in principle, you will have deposits of, whatever is in there. It may change the crystallization habits if that's what you're asking, because they can form co-crystals, and that may cause problems. That's probably the worst thing I would see. And the other thing is just the efficiency of the effect, right? If you have a magnetic sediment, it has an area. In some parts of it, there will be salt crystals, and in some parts of it, there will be REO crystals. And of course, the ratio between them, the solubility of the other, may affect things. But the worst thing that can probably happen is if there's, let's say phosphate that has to be there. And the phosphate changes the crystallization properties of RAO, which it doesn't, because I tested that. But, and then it doesn't become a conglomerate anymore. Then that can be a problem. Yeah.
Yeah, I guess I'm thinking of a different mechanism where maybe it's not possible, but maybe nucleation happens in solution, and then some of these microcrystals settle down to the bottom. And,
yeah. I mean, yes. So that can happen, but because of the kinetic preference at the surface, you have faster crystallization than you would have in the bulk, right?
Okay.
The barrier is faster if you pull it with the right spin. So in principle, if you do not have too high concentration, which would kind of make it like a kind of rain like a shower, it would make it rain. Which I expect, in a real scenario, the concentration to be much lower of the molecule. Then you're fine, because you have to be okay. So your question is actually really good in this sense. If you are above the solubility limit, like too much, then you just have crystals everywhere.
Yeah.
Right. You have to be slightly below, such that the kick from the surface makes it crystallize on the surface preferably.
I see. Yeah.
And
Gotcha.
that limit is probably way down in the real case, because I don't expect to have like molars of RAO in the lake,
Yeah. Exactly. Yeah. I remember there's work from Bert Meyer. I don't know if he's more of like a super molecular guy. He's not really prebiotic chemistry per se, but they've you can get spin polarized electrons when you attach I think they had DNA or something like that to an electrode surface.
Yes.
I was wondering, have you thought about using UV light in some molecule that can give up electrons upon
that's actually my first paper. My PNAS paper. Yeah, my first paper is about using electrons that are ejected from magnetic surfaces, which are spin polarized, to do some chemistry. And that was the first shot. And the idea is whether you get it from the spin polarization from chiral molecules, or whether you get it from magnetic sediments, you can get spin polarized electrons. And can you do chemistry in a chirally selective way? Let's say reduction chemistry.
Exactly. Yeah.
And in the paper, I call this cis-driven reduction chemistry, chiral induced spin selectivity driven reduction chemistry. one problem is, Albert, is that the efficiency is much lower, okay? Because you don't get a lot of electrons. Like photoelectric effect is very inefficient, because what happens is, as you kind of excite, electrons and create holes, the most favorable place for electron to go first is to go back where they come from. They go back to the surface and fill the holes.
Yeah.
Okay, so you don't get like a shower of electrons are ejected from the surface.
Yeah.
Yeah.
I got you. Maybe if you had some sort of organic photosynthesizer or something like that.
Okay. So those are interesting. Yes. So I'm thinking along those directions, and you can make asymmetric catalysis too, right? So if you can find like heterogeneously catalyzed reaction, then that can work too.
Yeah.
Also.
Very interesting stuff. Yeah. Let's see. The chat is full of comments,
I
but
see
I'm
some
not sure if there's
questions.
another. Do you see a question?
Yes. Egenos.
I think we've
What do you
answered all
think?
the questions.
There's one like orange. What do you think?
Oh yeah,
will-
right there.
Yes. So she's asking the discoveries that may arise. Well, I mean, we were kind of answering that with our discussion with Albert, right? So this spin selective interaction of between magnetic minerals and chiral molecules can be exploited in various ways. It doesn't have to be, of course, prebiotic chemistry, which, I mean, one application, but you can use it for asymmetric catalysis, which is a big thing. Perhaps, in biological systems, you can see it because biological systems use homochiral machinery to do electron transfer. I mean, the first thing that comes to my mind is the drug separation in pharma, right? A lot of drugs form crystals. Some of them probably crystallize as conglomerates, and you can use magnetic surfaces to separate drugs. So you can think of these applications.
Yeah, I guess you should probably patent your stuff if you haven't.
It is patented, actually.
Okay, very good. We have a question from Kevin again. Kevin, do you want to unmute yourself?
Yeah, just further on what you're discussing, Albert and Furkan, about how you would trap these electrons. If you had some sort of relay of porphyrins, like a sort of synthetic photosynthetic setup, if you're like an artificial photosynthetic setup, that might be the way to go. How you'd arrange it cleverly on the surface, I'm not so sure, but that might be one way of doing it, to overcoming the problem of electrons just bunching, and then, as Furkan says, dropping back into the holes, from which they were originally ejected from. So that would be a way possibly for doing it, I think. Something like that.
You need either that, or you can find a good hole quencher, which acts as a stoichiometric reductant and kind of provides more negative bias to the surface, so that there can be a net reduction, right? Because it's a futile cycle if you do not have a stoichiometric reductant.
Right. Okay.
So I actually am currently working on that direction a little bit more. Like, for instance, things like sulfides.
Yeah, I was going to say.
Can act as stoichiometric reductants. Like, I mean, the intuition, like one intuition is like, if you're familiar with the work of John Sutherland in regard to their photochemical cycles, they use electrons ejected from ferrocyanide.
Yes.
They recycle it back using sulfite or sulfide, so that there's a net flow of electrons, right? Without sulfite, the electrons ejected from ferrocyanide makes a ferricyanide, and then ferricyanide goes back to ferrocyanide by grabbing the electron back, right? So I'm working with like sulfide and sulfite. The problem with those is like, they tend to like stick to the surfaces. So they do not really, act as hole quenchers, but they kind of coat the surface.
Yeah, right.
So yeah, that either the first, idea, just coating the surface with some photosensitizer,
Yeah.
or using a reductant.
Yeah, definitely. Or a subtle combination of the two together would be very interesting. Well, because you've got that in photosynthesis, well, especially or you've actually got that in sort of the hemoglobin. You've got it's a ferrous ion complex by a porphyrin ring system. So if you could engineer that to sort of see what that would do under your experimental conditions would be very interesting.
Yes.
Absolutely. Yeah.
Thank you.
Just another follow-up crazy idea. There are reports that water droplets, very small water droplets that evaporate, produce hydrated electrons and hydroxy radicals at the surface, like as they evaporate, I guess. So thinking maybe if you had a magnetite nanoparticle in there, maybe you could generate a whole bunch of spin polarized radicals and
radicals. Yeah, that can be interesting.
Yeah, it's sounds like a fun playground.
Yes.
Okay, so we have a couple more questions in the chat. Then after that, I think we'll end the session.
Right. Let's see.
So I think this is for Shotaro, maybe, or I'm not sure if this is just a general comment, but are there trench-associated hydrothermal vents? I've had it in my head that vents are usually associated with spreading centers. That's still several times the pressure, but not like the depths of the Mariana Trench. Do you see the question in the chat? By Alex Deans Rowe? Or I guess there's an answer to it already, but.
Sorry, I couldn't find
Let's see. I can copy and paste it.
Sorry, are there trench associated hydrothermal? I've had okay. I've had it in my head that vents are usually associated with spreading centers.
Yeah, I guess the question is, where would you expect to see your supercritical CO2 mostly?
I have one slide to already discovered I guess this paper shows that this environment in this environment this liquid and supercritical CO2 discovered.
Yeah, okay, so you don't need very deep, just maybe like 1,000 meters or something.
Yes, around 1,000 meter.
Yeah. Yeah, okay, cool. Yeah.
Is it correct?
Yeah. Anyway, it's about that time. So I just want to thank both speakers again for very excellent talks. And yeah, I hope to see everybody back here in 3 weeks. So thank you very much, Furkan and Shotaro.
Thank you. Thank you, everyone.
Thank you.